O Lord, how manifold are thy works! In wisdom hast thou made them all. The earth is full of thy riches. So is this great and wide sea, wherein are things creeping innumerable, both small and great beasts. Psalm 104, 24 through 25. We're starting a new chapter today, chapter 6, titled The Survey of the Seas. We're going to be looking at oceans and seas. Not so much weather, that'll be in the next chapter, but some different things about really water in the ocean as well. So, yeah, this chapter is not very long. We're going to go through it a little bit quickly. We're just starting with the first section today, looking specifically at the water of the seas. Found on page 164, the ocean covers more than 70% of the planet's surface. The term oceanography means the study of the Earth's oceans. And then an oceanographer is a scientist who studies the Earth's oceans. And it has been said, and it's fairly true, we know more about the surface of the moon than we do about the depths of the oceans. We are still learning about it. The video series Blue Planet highlighted lots of things that we previously did not know about, and that there are scientists currently studying right now. One of the things not mentioned, not in that particular series of videos, but giant squids. Jules Verne talks about giant squids in one of his fictional works, and pretty much everybody just thought it was fiction until fairly recently when we actually found them in the deeper parts of the ocean. There's a lot still to be studied about the ocean. First thing, some facts here, characteristics of seawater. The oceans contain roughly 36 quintillion gallons of water. A quintillion is a 1 followed by 18 zeros. Although the water in lakes and streams is considered fresh water, it does contain some minerals, usually not in the way of salt, although in some places it is. We do have the Great Salt Lake, after all. Also the Dead Sea is extremely salty. Salinity is the measure of the quantity of dissolved salt in seawater. Pretty much how much salt is in seawater. That is what salinity means. And this includes more than sodium chloride or table salt. There are other types of salt, or there are salts made with other chemicals, I should say, and they are also found in the ocean. The salinity of seawater is not constant. There are several factors that will affect it. One is evaporation. The sun beats down on the ocean, water evaporates. This will actually increase salinity because it's only the water that leaves and the salt stays. Another is freezing. When the oceans freeze in the far north and the far south, it actually leaves behind the salt content. Only the water is frozen. So again, it reduces the amount of water in the ocean, thereby increasing salinity. Melting icebergs. That will decrease salinity, putting that water back into the ocean. The icebergs break off, they travel to warmer climates, they melt. Water from rivers. We mentioned that the river water is considered fresh water. There are some minerals in it, usually not in the state of salt, though. So this will dilute the water. This will decrease the salinity of water, especially near the mouths of those rivers, the mouths of the Columbia, Mississippi, other large rivers, Niles, the Amazon, so on. Salinity varies from about 3.3% to 4%. Around the world. 3.3% is closer to the Arctic Ocean. 4.0% is around the Red Sea, near the Red Sea in the not Gulf of Mexico, wrong Gulf, but Persian Gulf over there in Middle East. 78% of the salt in the ocean is sodium chloride, the same stuff that sits on your table for dinner. Ocean also contains dissolved gases. If it didn't, the fish would die because they would need oxygen that is dissolved in the water. Fish gills do not break apart water molecules to get oxygen. They simply filter out the oxygen that is present in the water. So, color of ocean water is naturally blue. A small quantity appears to be, when you only have a small amount of it, it appears to be transparent. But as we collect more and more, we do get that blue color. Now, it does vary depending on the depth of the ocean that we're looking at. depending on other factors in the ocean, stuff like that. The surface temperature varies widely with latitude, 28 degrees Fahrenheit to 86 degrees Fahrenheit. Those colder temperatures are going to be near the Arctic and Antarctic, right? And the 86 is going to be closer to the equator, and pretty much everything in between. Now, some places it is more seasonal. Certain times of the year, the ocean temperature will change quite widely. Some places it's pretty consistent. Within the ocean, even as we go up and down in the ocean, there are cold and warm water. You may have experienced this kind of before if you've ever swam in a river. You may have experienced some cold water pockets or something. This is a little bit more pronounced than that in the ocean. The thermocline is the region where cold, deep water meets the sun-warmed water near the surface. Remember I said the sun beats down on the ocean, it warms up the water, even evaporating it. Well, there is kind of a threshold there. As we go down, eventually we find the area where there's a boundary. And underneath that boundary is cold water, and above that boundary is warmer water. It still might be kind of cold, but it's warmer than what's below it. Another factor of seawater is density. Two main factors affecting density are temperature and salinity. The colder the water is, the more dense it is, and this is because of the way molecules act. Colder temperatures cause molecules to stay closer together, and so more molecules pack into a smaller area. This is density. Density is the amount of matter in a specific area. Salinity. The more salt water contains, the more dense it will be. So the more salt there is in the water, the more dense it is. And that's because salt is pretty closely packed together too. So even though it displaces some water molecules, the salt really makes up for that in the terms of densities, causing it to be more dense. So colder or denser water, colder or more saline water will be denser. This will actually cause it to fall. We actually get currents because of density. And these are currents that usually flow well below the surface, deep currents. These are not the currents that we normally talk about as far as like paths that move seawater around the surface. Another factor of the ocean is its pressure. We call it hydrostatic pressure, and that's just pretty much the pressure of being there. Hydro means water, static means staying the same. So it's simply because of the fact of water there. We have talked about, or we've mentioned air pressure before at 14.7 pounds per square inch. And pounds per square inch is the measurement of pressure. It's a weight over an area. So pounds per square inch. For roughly every 33 feet of water, 10 meters of water, we increase by what's called 1 atmosphere, or 14.7 psi. This adds up quickly. For the average swimmer, not too big of a deal. Even the average scuba diver, not that big of a deal. Our bodies are designed to accept quite a bit of pressure change, actually. And going down 100 feet in the water is doable for humans. Our bodies can take that kind of abuse. However, we have to be careful about returning to normal PSI. We can go down pretty quickly. We can increase pressure pretty quickly. Our bodies can withstand that. Decreasing pressure, on the other hand, we have to go carefully. There is a disease called the bends. Disease isn't technically the right term, simply because it results from the gases in a diver's body expanding too quickly. As they come up out of the water from deep depths, the pressure on their body decreases, gases in the blood start coming out. This isn't really a big problem as long as they come out slowly. It's when they come out quickly that it can actually even cause death. So, like I said, it adds up very quickly, and divers have to be, if they dive deep, they do have to be careful about how fast they come back up. So, this is one of the reasons why getting to the very bottom of the ocean has been problematic, is that amount of pressure that's down there. By the time we get down to the bottom of the ocean, we are talking about thousands to tens of thousands of pounds per square inch. The best stuff we can make cannot withstand that, or at least not easily. We have designed a couple, I think there's 2 or 3 submersibles that can go down to the deepest part of the ocean, but they're expensive to run. There's other problematic issues with it, so we can't do it very often. Hence the reason we still don't know everything we can know about the bottom of the ocean. On the surface, we have ice of the seas, page 167. There's a couple types of sea ice here. Freezing point of seawater is around 28.8 degrees Fahrenheit, which you might realize is lower than the normal temperature that water freezes at. This is because of the ice, or because of the salt in it. It has to get colder in order to freeze. Sea ice is usually not salty. When seawater freezes, it leaves, whoops, I wrote that wrong. When seawater freezes, it leaves the salt behind. That should say salt, not ice. When seawater freezes, it leaves the salt behind. Now, the 2 types of ice that we see. There are icebergs. These are huge chunks of floating glacial ice. There's a couple different, or 2 different types here, basically. One is Antarctic icebergs. They tend to be flat-topped and straight-sided. What you probably pictured, and what I have a picture of here, is probably an Arctic iceberg. They tend to be jagged and peaked. Icebergs float because they are slightly less dense than seawater. When water freezes, remember I said that as water gets colder, the water molecules get closer together. Well, something phenomenal happens when it actually gets to that freezing temperature. Instead of getting as close as they can, they actually pop apart almost a little bit. And now they actually take up more space than they did before they froze. So once they freeze, they actually take up more space. This makes it less dense. And if it is less dense, then it will float. I've heard it said before that roughly only 10% of an iceberg sticks out of the water. It probably depends on the shape, the mass, and a couple other factors, but that's probably pretty close to that. And you can see in this picture here that there's the iceberg, and then there's this little boat down here. And I believe that is just a little motorboat. I can see the guy standing in it. But to give you kind of an idea of how big these icebergs can be. The other type of ice are ice shelves. This is when pretty much a continental glacier reaches the end of the continent. The outer edge of a glacier that floats on the ocean's surface. So there is no land underneath it, it just simply floats there. These are usually what will break off to eventually form icebergs as well. Those are really the 2 types of ice that we see on the ocean, are icebergs and ice shelves. Really, the only ice shelves that we're going to see are off the continent of Antarctica. There are possibly ice shelves, smaller ice shelves off of Greenland and some of the parts north, possibly off of Alaska and northern Russia as well. So, yeah, that is where we will leave it today. And your video question goes back to the pressure there. About how many feet of water gives us 14.7 pounds per square inch? How many feet of water results in 14.7 pounds per square inch of pressure?